Okay, guys, so today we will be discussing now the procedure on how to deal with the laterally braced beams in the LRFT code. Okay, so this is more on the procedure on how to take care of problems concerning laterally braced beams. Note that the laterally braced means that the beam is prevented to experience um, lateral torsional backlash. Okay? It is prevented, so this will actually ensure us of a behavior with no lateral torsional backlash. And the definition of compact and non-compact sections will now be the main agenda for the procedure. No? So your requirement for compactness, okay, is our main focus in this regard. Okay, so when you say compact, all we have to do is to check lambda r and lambda p. Okay, wherein lambda r is simply the non-compact limit and lambda p is actually your compact limit. So the definition of uh, a slender column now will actually be in the boundary, within the boundary of the non-compact limit, wherein those which are not uh, complying with the non-compact requirement will be called slender, and those which will at least pass the uh, the requirements for non-compact limit but does not pass the requirement for compact limits will fall into what you call a semi uh, compact or partially compact section. Okay, so this uh, limit for the width to thickness ratio are based on the plate stability concepts that we have discussed earlier. So I gave a video on plate stability if you want to uh, have a very detailed idea on how a plate stability works, no? In steel sections, then please watch the video. Okay, so where do we get this lambda p and lambda r? To start with, we need the same table that we use for columns. No? So this is now table B4.1. If you still remember this lambda r, uh, upon which we define our local backlink limits, okay, in columns. So it's just the same. But of course, the cases will be more defined on the flexure, okay, on the flexural behavior, because these are intended for beam behavior. Okay, so all we have to do is to come up with lambda r and lambda p Okay, and compare it with the actual width to thickness ratio here. So if it is less than lambda p, then we say that this is a compact section. And the following are the factors that are now used in the process of determining your nominal moment capacity. No? So these are now the conditions that sections must have their width thickness ratio not exceeding lambda sub p. And if we recall, lambda sub p is simply the upper limit into which your section is selected to ensure that the element is capable of very large plastic strains prior to local buckling. And in this type of behavior, your section are expected to achieve uh, the plastic moment that I discussed again on the previous video. So this is now your moment versus lambda, wherein your plastic behavior falls within, okay, this value of MP. Okay, so your lambda P is now this value. So if your section is less than or equal to lambdas of P, you are assured of a plastic moment capacity for your Mn, which can be computed very easily by simply multiplying the plastic modulus with that of Fy. Okay, for the non-compact limit, so which is higher, no, than lambdas of P here, so this becomes, okay, your point, the limiting point, upon which your definition for partially compact, so this is now the partially compact or the semi-compact, this is now the compact, will be defined. The partially compact and the slender behavior will be referred to, no, in this particular value of lambda r. Okay, so the conditions are such that the sections whose element width to thickness ratio equals to lambda r, and therefore defines the behavior upon which your partially compact section and slender section is defined. But if you want to get the equivalent capacity of this, okay, so this is now a boundary, no, between your partially compact section and slender. You have now your MR, which is defined as your um, residual moment. Okay, so your Mn now becomes your MR, defined by on the basis of your yield moment minus your residual, uh, your moment due to residual stress. And if we look into the formula, your moments is now converted into stresses. No? So your yield moment will be equivalent to your yield stress, and your residual stress will be converted to your your residual moment will be converted to your residual stress, and your MR is simply the remaining, no, the remaining moment, okay, in uh, remaining moment after your residual moment has been deducted. Okay, so if I ask you what's the residual moment equivalent, simply use this formula. And for the partially compact, we have again some conditions to meet. So sections whose element width to thickness ratio is in between lambda p and lambda r, and the capacity is obtained simply by assuming this to be a straight line. Okay, so this is linear, and therefore it can be solved on the basis of ratio and proportion, or simply linear interpolation between MP and MR. So this is now your linear interpolation formula using a simple ratio and proportion. Okay. Of course, this interpolation should not exceed the value of MP here to prevent over estimating your nominal moment. And for the slender section, lambda is greater than lambda r, conditions of which the sections whose element width to thickness ratio exceeds lambdas of r, and this must be treated in accordance with the LRFD Appendix B using a shape factor or a reduction coefficient Q equivalent to QA QS. So there's a formula I have not placed here, but we'll try to look into it uh, later. So I did not give it because I want you to take note that the slender section is not a very good section to deal with. So always we must avoid such design of steel sections behaving within this range of slenderness. So that's it for the general procedure on how to approach a laterally braced beam in terms of compactness requirement. Thank you very much, and I'll see you on the next video.